so before we dive into our presentation, the image up here is just everything that is in this box, which is our actual box that we're going to be setting up for those of you sitting further away. So my name is Daniel Cooke, as our mentor said, and this is my partner, Weisensee, and we're working with the payload construction, and our presentation is called View from Above.
A quick history of the DemoSat program. The DemoSat program is sponsored by Colorado Space Grant Consortium. They've been doing payloads since 2004, and they've been in existence since 1989. As you can see on the far right, there's the balloon, and underneath is the flight string and payloads, and that's a quick drawing of what exactly is going to be going on. Our main purpose is to design, build, and test a module that can record data at the extreme temperatures and conditions of the upper atmosphere. We'll be facing super cold temperatures, low pressure temperatures, and things of that sort. Since 2004, and ever since UNC has been a part of this DemoSat program, groups have had to reinvent these payloads or reinvent designs for the modules. So another one of our main goals is to make a foundation for future years to build off of.
And so you have your payload, and to build your payload, you basically need a set of materials. And the first one we have is our heating system. And the heating system is composed of 8 batteries connected to a heater to heat all the electrical components that is within the box, within the payload. And then you have your altimeter, and the altimeter is going to be used to gather pressure and altitude. And then the Arduino Uno is going to be used to gather the data from the altimeter so that we can put it on the computer and analyze it. And then we have a camera, which is going to be used for video recording. Next is our plexiglass on the bottom right corner over here. And the plexiglass is basically used for lens protection. And on this box, on this module, it is actually on the bottom right corner. I don't know, on this top side here. And then we have our dry write, and the dry write is basically used to help the lens from clogging. And so before we build our payload, we had a lot of choices and issues that we had to come over. And so we chose for our camera, we're using the Contour HD, and they recommend 16 gigabyte, but you can put a 32 gigs on it because our flight is 3 hours, and so we need as much video as we can get. And so what the 32 gig will do is, if you have a 32 gig, it'll record all the data, but once the 16 gets filled, the camera will tell you that it's full, but it's not really full, and it'll just start a new program and start recording again. And so if you have that extra space in there, then you have more data to collect. And then we use at first we're mostly focusing on on the video. And so what we spend a lot of time talking about is a convex mirror, or something like a ladle, which is just this, that we can use. And like on the picture over there shows, the ladle would be somewhere on one side of the box like this, and then the camera would be inside of the box. And so the camera will be at an inclined position looking at the ladle, and then it will be getting the views from both sides as the picture shows up there. And so for this project, this Colorado Space Grant Consortium told us that we had to meet a weight limit of 1.5 kilograms.
So when you're trying to keep something warm, it's best if you use a heater. So this is our heater. This heater is ran by 8 9-volt batteries, and the actual heat is produced by 1 kilo ohm resistors. And the way a resistor works is, I'll show you this too, is basically electric current runs through these wires, and it goes through these big whitish blocks, and these whitish blocks pick up electricity, and they resist the flow of the current. And as they do this, it actually produces heat. Now, one of the issue we had was deciding how to put the batteries. So I look on the far right, there's a switch. On the top is your resistors, And if you get the bottom right side, right here, there are 9-volt batteries in parallel. And there's two 9-volt batteries in parallel, which are equivalent to 18-volt batteries. And there are 4 18-volt batteries in series. So this design, the circuit diagram, shows a design that would get warm, but it wouldn't get very warm. It would just get kind of warm, and it would last for a really long time. This is in comparison to the design we're actually going with, which has 4 9-volt batteries in parallel and 2 sets in series, which is equivalent to 2 36-volt batteries, which gets hot very quickly and doesn't last as long. But since our flight duration is only 3 hours, this actually will last around the 3 hours that we need, so it is more like what we need.
And so in your box, in the payload, there's a lot of things in here, and each thing has a different center of mass, different calculations that have to be done. And so the equation on the bottom left here is the center of mass equation that we use to calculate everything, since they do all have different masses, lengths, and weights. And so what the center of mass equation is basically telling you where the center of the center is. I don't know, that sounds kind of weird, but it's like the center of the center. And so it's like you have all these things, like you have you have something that weighs 4 pounds and something that weighs 2 pounds, and other things that weigh like 0.5 pounds. And you have the 4-pound thing and the 2-pound on one side, and you have the 0.5 pounds on another side. It won't be really straight. And so if you're trying to record video at the same time, your camera viewing space is going to be really weird. And so insulating the box, as Joe mentioned earlier, it gets really cold up in the atmosphere. And so what we used is basically we have fiberglass, which is the yellow coating, and then that basically is like keeps the box warm. It's like the warmest thing in there. And then we use the aluminum tape, which is the shiny outside, just this stuff right here. And that keeps everything in and everything out. And what that means is it keeps stuff like radiation and vapors out of the box in higher altitudes, because there's a lot of them up there. And it keeps the heating from the heater inside of the box. And then we use foam core, which you can't see, but if I'm outside, you can kind of hear it. And it's basically just like the strongest part of the box. Once it lands, like everything's still somewhat together.
One of the main things we did was called soldering. I don't know if everyone knows what soldering is, but a brief description. Soldering is very similar to welding, in which you heat up a piece of metal to connect electrical components.
And so on the photo on the far left here, we have one of the heaters that we built and tested. And what it basically is, you just squeeze the one of the wires, like the red one, is squeezed on one of the electrical side of it. And you can't see this on the other side of the photo, but it's like one of these ends of the resistors. You take a wire like the black one and you solder it to a piece of wire, so then you're able to connect it to stuff like batteries or an on-off switch to get it to heat up and stuff. And then on the top center, we have our soldering kit, or the hot iron. And then below that we have, it's just an instrument we use to hold the breadboard down, which is this material that the resistors are on top of. And so you have it holding this, so then it's like this, you're able to solder, so you won't get stuff on your hands. And then the picture on the far right is our undo button, that we like to call it, because you're going to make mistakes when you're trying to solder. So if you have an undo button there, it makes life a lot easier.
Another thing we have is our altimeter, and the altimeter is actually this little blue chip that's on the Arduino board right now. The altimeter takes barometric pressure, which is how dense the air is, in a sense, and it uses that to determine altitude. It also records temperature, which is just kind of a side thing, and it's kind of nice to know what the temperature of your box is as you're going up, because past a certain point, your electrical components do not work. So before Colorado Space Grant Consortium would allow us to send our payload up, we had to conduct a series of tests. All we were looking for on these tests was the minimal success criteria, the bare minimum of what they had to pass. And in some senses, that's what we took. In some senses, we took it to the extreme. The tests in bold up here, the drop test, the cooling test, and the fog test, we're about to go in more detail. This is our test box. It is right here. If you see the circles that are on top of the box that's on the screen, those are weights that total 1.5 kilograms. And this is to simulate what the box will do under full weight conditions.
And so a view from the roof. What we basically did was, this is what we call our drop test. And so Colorado Springs Grim Consortium told us that we had to test our box from 20 feet. But here at UNC we go hardcore, so we took it 4 stories. And on the right, that's the image of the box at impact, so once it hit the ground. And what actually happens is, if you look at it, you'll see a piece of tape coming off. But what that did was, it's one of the weights that flew off once the ground hit, once the payload hit the ground. But that doesn't really concern us so much, because everything in our box is in our box, even the on and off switches. And so we don't have to worry about stuff like that happening.
Another test we conducted was the cooling test. We called it the liquid nitrogen test. In this picture up here, you see a styrofoam box, and in the styrofoam box is our payload. If you see these black wires, those are different probes that measure temperature. And one probe we had sitting at the top of the box to the top of the styrofoam box in order to tell what the temperature was outside the box. We had a probe right next to the heater that was inside the box. We had a probe that was just inside of our box. And so here's the liquid nitrogen being poured into the styrofoam container. It just shows that it got cold pretty quick, and then we put the lid on for about an hour and a half. And so we got some results. If you look at the green line up here, the green line shows what it was like next to the heater. It started off warming up, and then temperature kind of took its toll. The yellow line shows inside of the payload, and the blue line shows outside the payload. Now, the reason that the blue line, which is outside of the payload, is a higher temperature than the yellow line, which is inside the payload, is because the temperature that the blue probe was measuring was at the top of the box and was only measuring the vapors, whereas the orange line had a probe that was closer to the bottom and it was getting more of the liquid nitrogen. And this spike right here in the blue line is not natural. It's something we caused. We weren't sure which wire was which, so we grabbed the blue one and heated it up. And over here is really the raw data. It takes the temperature over a series of time, and that's how it gets the numbers for what it graphs. Another test that we made was the fogging test. So this test wasn't actually mandatory, but we're sending a module up that requires a camera. Well, not really requires, but we're using a camera. And if we want this camera to take pictures correctly, and if the lens is all fogged up, you can't really take pictures correctly. So underneath down here is a stove, and on top of the stove is some water, and on top of the water is a filter, and on top of the filter is dryerite. Now dryerite is anhydrous, which means it has no water, and it is made of calcium sulfate. So basically, whenever water vapors go up, this dryerite, which lacks water, seeks to find water to make it more complete. So as the water vapors go up, the dryerite absorbs water. So we placed the camera right above the dryerite and saw how much fogging, and fogging was greatly reduced when we put dryerite in.
And so this is just some of our references, all of our references that we used.
And our acknowledgments. We'd like to thank Dr. Matthew Seamak and David and Amber for helping us our research. We'd like to thank Maurice for being our advisor, and I'd personally like to thank the Morris family for providing me the opportunity to attend this trip, and the Edward Madigan Foundation for allowing me to do research.
I would like to personally take this time to thank Suncor Energy for providing me the time to be here, and the Kinder Morgan Foundation for sponsoring my research.
And we'd both like to thank our family and friends back home, and our friends here, for encouraging us and supporting us through this journey. Thank you.